In this video, we'll be continuing to look at the preparation of organohalides from alcohols, but we'll be looking at alcohols that do not go through the SN1 mechanism and instead go through an alternate mechanism. In an earlier video, we saw examples of tertiary alcohols reacting with HX to undergo substitution. And we also saw that secondary alcohols can undergo reaction with HX to give the substitution product. And we also talked about how these will undergo the SN1 mechanism, which proceeds through a carbocation. Now, we also saw that a primary alcohol could undergo substitution, and methanol can also undergo substitution. So we know that this reaction can work on tertiary, secondary, primary, and methyl alcohols. However, we also saw that tertiary carbocations are more stable than secondary, more stable than primary, more stable than methyl. We also saw that the transition state leading to the tertiary carbocation would be lowest in energy. The transition state leading to the secondary would be higher, the transition state leading to a primary even higher, and the transition state leading to a methyl carbocation is going to be extremely high in energy. Given that formation of the carbocation is the rate determining step in an SN1 reaction, what this means is that an SN1 reaction of a primary or methyl alcohol is going to be extremely slow, because trying to form this carbocation requires a huge activation energy. Very few molecules will have that energy, and so the reaction will proceed very, very slowly. So we know that the substitution reaction can work on methyl and primary alcohols, but it also is unlikely that it will proceed through the SN1 pathway. Also recall that we looked at some experimental evidence that showed that for tertiary alcohols, the rate was equal to the rate constant K times the concentration of the alcohol. And this is what we found with the SN1 mechanism. But we also saw that for methanol, the rate was equal to a rate constant K times the concentration of the alcohol times the concentration of HX. So this is evidence then that the reaction of methanol proceeds through a different mechanism. So not SN1, it must be something else. We can see why it doesn't go through SN1 because this is going to be way too slow. So there's another pathway that is more reachable for methyl and primary alcohols. So if we think about the reaction of methanol with HCl to form chloromethane plus water, let's think about how this reaction can proceed. The first step, where an alcohol grabs a proton from HX, that is a very easy step, so that can work with a methyl alcohol as well. These electrons move on to the chlorine, and so our first step gives us this, where our oxygen has a positive formal charge plus Cl minus. Rather than proceeding through the formation of a carbocation, which would mean that this oxygen takes the pair of electrons that it's sharing with carbon and steals them to itself. Instead of that happening, the chlorine can act as a nucleophile in this step. So if chlorine attacks the carbon, that will push away water as a leaving group. So that gives us the chlorine connected to the methyl, and we have water as our byproduct. So this would be the reaction diagram if this underwent an SN1 reaction. So going from methanol to protonated methanol is easy, but forming a methyl carbocation would be really, really difficult to do. So this has a huge activation energy. On the other hand, if we go from methanol to our protonated methanol, and then if chlorine attacks in this step, so we do not go through a carbocation intermediate, instead the chlorine attacks. So in our transition state, it's going to look something like this. So here's our hydrogens. Here is our oxygen carbon bond breaking, and here is our carbon chlorine bond forming. So the chlorine will have only a partial minus, not a full negative charge. The oxygen will have a partial plus, not the full positive charge that it had here. Will be somewhere in the middle where bond forming and bond breaking are occurring. Then as we proceed to the products, this bond completely breaks, this bond completely forms, and what we get is our product. So often reactions can go through different pathways, but if the protonated methanol had a choice of climbing over Mount Everest to eventually get to the product, or it could just have a lovely hike up Mount Diablo to get to the same product, most likely it's going to pick the easy Mount Diablo hike. So tertiary and secondary alcohols can undergo an SN1 reaction because although formation of a carbocation is difficult, it's still achievable. Methyl and primary alcohols will undergo a different mechanism because it's too hard to form that carbocation. So the first step is exactly the same, protonation of the alcohol. But then the second step is what happens in an SN1 reaction in two steps. Here it happens all together. So this is still an easy step, so that this is the activation energy of step 1, but now this is the activation energy of step 2. So step 2 is the rate determining step. And if we look at the transition state for the rate determining step, we see that there are two molecules involved. So two molecules involved in the transition state of the rate determining step. That means this is a bimolecular reaction step. So this reaction proceeds through the SN2 mechanism. Substitution, because that's the overall change that happens. Nucleophilic, because the chlorine acts as a nucleophile, pushing away water as a leaving group. The 2 stands for bimolecular because there are two molecules involved in the transition state of the rate determining step. So as we think about the overall reaction of an alcohol with HX to form RX plus water, we have two different mechanisms. For SN1, we have step 1, alcohol plus HX gives protonated alcohol plus X minus. And step 2, our protonated alcohol forms a carbocation plus water. And then step 3, our X minus reacts with our carbocation to form the alkyl halide. For an SN2 mechanism, step 1 is exactly the same. But in step 2, we have X minus reacting with the protonated alcohol. I'm going to have to write this down to give XR plus water. And so The first step is exactly the same, but for SN1, we have steps 2 and 3, whereas for SN2, those two steps are combined into a single step. Now we're going to look at other examples of SN1 and SN2 reactions, and so the rules are going to differ just a little bit. But specifically, when we are talking about this reaction, a tertiary alcohol will undergo the SN1 mechanism, not the SN2. A secondary alcohol will undergo SN1, not SN2. Why can't they undergo SN2? The rate determining step of the SN2 reaction is nucleophilic attack of the nucleophile on the R group to push away water. If this is a methyl group or if it's a primary alkyl group, then the X minus can fight past those hydrogens or that carbon to get to the carbon that has the leaving group. But if we're talking about a tertiary or a secondary alcohol, there is too much steric hindrance. So this nucleophile cannot reach the carbon that is connected to the oxygen, so it can't go through this in a concerted approach. It has to do this stepwise approach where we go through formation of the carbocation. Tertiary and secondary alcohols will undergo SN1, not SN2, because they are too bulky for a concerted step 2. Primary alcohols will undergo SN2, not SN1. Methanol will undergo SN2, not SN1, because the carbocation is too unstable. So for a tertiary or secondary alcohol, it's easier to go through a carbocation than it is to try to have that nucleophile fight through those bulky groups to carry out this reaction. For a primary and a methyl alcohol, they go through SN2 because it's easier for the nucleophile to attack here than it is to form the carbocation. So a moment ago, I gave the example of Mount Everest versus Mount Diablo, but the thing that's important to remember is that which pathway is easier depends on the structure of the alcohol. For some of them, it's easier to go through one pathway and it's hard to go the other pathway, but for others, it's easier to go the other pathway and harder to go the first pathway. So this is why different alcohols will proceed through substitution by different mechanisms, leading to different rate laws.